Good afternoon. I'm going to first quickly introduce our panelists. My name is Acharya. I'm the moderator. I'm at the National Science Foundation, IIS. I'm a program director, and I'm a faculty at Indiana University. So,
Hi, I'm Nikunj with NASA. I lead the data sciences group there. We do, pardon me, we do machine learning R&D for the full range of NASA problems. So this includes aeronautics, earth science, space science, and human space exploration. I also have been leading a project involving machine learning for aviation safety and also adding other components to that, like human performance and fatigue, and also identification of human contributions to safety. Thank you.
Is this on? Can you hear me okay? All right, great, thank you. So good morning, everyone. My name is Jarvis Haupt. I'm on the faculty here at the University of Minnesota in the Department of Electrical and Computer Engineering. I'm also, I guess, I have a couple administrative kind of sections too. I'm associate department head, and I'm also the chair of the editorial section of electrical engineering and systems science at Archive. So among other things. So my research interests are broadly in signal processing. That's sort of been my path since I was in graduate school. And back then, signal processing meant kind of something, I think, a little bit more focused. But in recent years, like everything else, it's broadened quite a bit. So, you know, I dabble in things like optimization and machine learning and data science. I created a machine learning data science course for our department a few years ago. So, you know, my interests in AI are also kind of multifaceted. So recently, we wrote a paper for the IEEE Signal Processing magazine on using AI for signal processing education. So I'll kind of draw on some of the insights that we uncovered in that effort here. So I'm excited to do this. Thank you.
Good morning, everyone. My name is Lior Horesh. I'm a senior manager at IBM Research, leading the mathematics and theoretical computer science group. Part of our mission is to advance computation in general, but in particular in the domain of AI. We have doubled our efforts on trying to bring statistical AI and formal methods together, specifically for scientific discovery. So hopefully that background will be relevant to this conversation.
as a background, today in this panel, we'll be discussing algorithms and methodologies for creating AI testbeds for real-life situations. At NSF, we had an AI institute call last year. It's called Strengthening AI. And the whole idea was we just gave the specs. And the specs was grounding. That's the fundamental principles on which the AI algorithms was based on. The second one was alignment. Alignment basically meant, does it align, the output align with what we expect as humans? And the third one was instructability. Instructability is, can the algorithms and methodologies learn from humans and other AI systems? So what we're going to do is sort of have that in the back of the mind. And we have about 7 questions I have. I will ask the panelists. I've chosen which one answers the particular question. After we finish the 7 questions, we will open it for the audience to ask questions. So the first question will be for Jarvis. And the question is, how can we ensure that GenAI models for science not only generate realistic outputs, but also respect physical laws, support logical reasoning, and provide scientifically grounded explanations? Can these models be formally verified? And how do we distinguish between hallucination and genuine novelty?
All right, so thank you. So in full disclosure, we had these questions a bit ahead of time too. So I've had a little bit of a chance to digest some of these. So I'll take them in parts, and I'm going to refer to Raj's screen here just to remind myself the different parts. So the first one about generating realistic outputs and respecting physical laws. I think one of the things that so every year I teach this machine learning course, and I kind of anecdotally poll the students and say, how many people use AI and what do you use it for? And over the last couple of years, of course, this has grown exponentially. And their sort of interests are not exactly what I would expect. A lot of them say they'll use it to do things like, I could say something like transcoding. They'll take a section of text from the textbook and say, explain this to me in a Gen Z way or something like that, as somebody told me once. So the use cases are sort of diverse, but one of the things that I always try to impress on the students too at that point in that conversation is that AI shouldn't be seen as an oracle, right? So bringing that back to the context of this question, how do we make sure that we respect physical laws and have scientifically grounded explanations? So the first one is not to overestimate the tool. These things are amazingly powerful tools, but if you ask it to take a large composite number and factor it into two primes, right, the essence of like RSA decryption, you can't sort of do it, right? I mean, it's not like it's going to look back in a pattern of human knowledge and say, oh, here's a connection that's going to let me do this. These are kind of known to be hard problems. So I think that has to dovetail with the validation schemes that we use, right? There has to be physical validation on some of these things. I mentioned this article that we wrote, and a couple of the things, the challenges that we were looking at with that were the same as in scientific endeavors that arise also in the educational space. So you say, how do I make sure that I'm giving proper, correct educational content to somebody, generating it with an AI tool? And the couple of things that come to mind are, one, you have foundational credibility. This comes back to kind of appealing to physical laws and saying, if I have a principle, I have a fundamental equation and I can verify that and I can demonstrate that it's being verified. And one of the ways that we kind of advocated doing that in the paper was creating something like JavaScript applets that you can do in kind of a no-code approach using AI to demonstrate these principles. And the other one is vicarious credibility. So in an educational space as well as a scientific space, it's important to see that what you're getting are kind of data from reputable sources. You can query the AI and say, only give me kind of insights from highly cited resources or something like this. And you can kind of quantify some of these efforts. So I think some of those same ideas translate to using these in scientific applications, that we can appeal to these notions of foundational and vicarious credibility. And it might just come down to also kind of doing the hard work of verifying these things ourselves, maybe in an automated fashion. But the last thing I wanted to mention here, because I want to save time for everyone to answer their questions, is the question here about how do we distinguish between hallucinations and genuine novelty. To me, I think this is a fundamental question in science in general. And the way that we've done this throughout history in kind of our disciplines is a peer review process, right? There's this notion of humans need to somehow be in the loop to double check things. Even if you have a theorem that's proven, you'll put it up in archive and people will look at it and say, oh, there's a loophole here, or you missed something there, or whatever. So there's a constant validation process going on in science. And to me, I don't see necessarily that when we automate sections of this, that whole process, that pipeline breaks. I think it might change, it might look a little bit different, but I still think humans in the loop is a kind of a critical part of the validation scheme overall.
If not, go ahead.
No, so I just want to add that indeed, one of the things that we see is that GenAI is not a end-to-end solution necessarily, right? We have to think about it as a tool that has some great virtues, but also fundamental limitations. At least at the current capabilities of GenAI, it is a good idea to think about complementarity of GenAI with other maybe formal tools or other machinery in order to make sure that hallucinations and other implications of not necessarily following or adhering to all physical constraints are indeed satisfied.
I think in signal processing, there is a famous saying that you cannot beat the sampling theorem. And the only way you can beat the sampling theorem is with a priori knowledge. Hallucination is created because some sort of sampling is violated, right? So from an information theoretic point of view, this is sort of an approach one could take on why hallucinations are generated and how do you mitigate them. So I'll move to the second question. what new principles and frameworks are needed to evaluate GenAI models in science, especially with respect to uncertainty quantification, out-of-distribution generalization, reproducibility, and hypothesis validation.
Thank you. So yeah, this in some way also relates to the first question, but while we want to respect physical laws and the like, we don't want to have too much respect. I guess, yeah, so I mean, as you know, Box, the greatest modeler, as he said, you know, all models are wrong, but some are useful. And it's more fine-grained than that, right? Different models are useful to different extents in different operating regimes. And in some cases, we just don't have any idea. So we don't have any kind of model or human knowledge or the like. So ultimately, it's going to boil down to some kind of like a mixture of experts. Sorry, I did my PhD in ensemble learning, so I tend to think about ensembles and committees and the like. So ultimately, it boils down to kind of like almost what we do, right? We know different people's expertise. And so in this case, we know we can figure out different models' expertise, whether it's data-driven models or physics-based models, and use them in ways that are appropriate. Thanks.
Thank you. Any questions, comments from the panel? Okay, Lior, I will have the next question for you. Which Gen AI approaches, such as diffusion models, autoregressive models, VAEs, normalizing flows, or GANs, are best suited for different scientific problems? What criteria should be guide for these choices?
Okay, so first of all, maybe let's start with the criteria, because obviously there are different tasks and each task has different emphasis on different properties. So one question is what type of data we are dealing with. What is the volume of the data? What is the quality of the data? For instance, GANs require a lot of high quality data sets, while VAE can actually work with relatively small data. What is the dimensionality of the data? Are we talking about voluminous, large dimensional data that typically can be handled with diffusion models or poorly with normalizing flows? What is the structure of the data is even more relevant, right? So if we have sequential data, obviously autoregressive type of approaches would make more sense. If we have tabular data, we often resort to VAEs. If we have continuous space type of data, diffusion models, normalizing flows are typically more appropriate. Now, the next question is what type of scientific requirements we have, right? How important it is for us to incorporate some physical constraints or laws, and normalizing flows seems to be one of the better approaches in terms of being able to encode those exact conservation laws. Diffusion models can do that also, but more in the form of guidance. And we can also do things of that nature with VAEs. We can work in the latent space and incorporate some of our knowledge in one way or another. Uncertainty quantification is another big question. So if we are really careful as for exact representation of uncertainty, we may want models such as normalizing flows that allow us to exactly estimate the likelihood and the posteriors. VAEs can also enable us to do that with a lower bound and approximations, but obviously there are different propositions in that regard. Interpretability is another big question in terms of scientific criteria. How much we care about whether we understand the intrinsic relationship, or we are happy with a black box that can provide us good input-output relations. VAE is one of the better options in terms of interpretability. And I guess it was also mentioned in the previous talk, controllability is another important virtue. Then, of course, there are also questions related to computation, right? So if we care about generation speed, we may choose approaches that are more scalable computationally. We may want to care about training stability. GANs, for instance, is not the best approach for training. Do we care about memory requirements and so forth? Now, when it comes to the question as for what type of applications each one of those models are excelling at, so if we think about diffusion models, they are really doing very well when we deal with high-dimensional data sets that have complex multimodal distributions, and that seems to fit rather well molecular conformation sampling, protein structure generation, and any other problem where we have some sort of continuous underlying physical law that is governing the behavior, and we are happy to search in that sort of vicinity. Autoregressive models, as we mentioned, are very useful when we look into sequential data. So whenever we have causal elements, whenever we have time series or a reaction pathway predictions, problems of that sort would be very natural choices for autoregressive models. When it comes to VAEs, they are rather interpretable when it comes to the latent space. So problems like chemical space exploration, dimensionality reduction, when we have a high throughput of experimentation, they seem to be very appropriate for these classes of problems. Then, sorry for the long list, but I try to hopefully address all of them. When we talk about normalizing flows, they have a wonderful ability to represent conservation laws, and that may be a good fit for problems where such conservation laws apply, right? So problems that involve thermodynamical relations or other conservation laws such as the phase space sampling and so forth. Lastly, per GANs, I'm not a big fan of GANs, so I hope that I'm not trashing them unnecessarily. But when we do have abundant data, we have a lot of data, we would like to explore a large space, we would like to generate a lot of synthetic experimental data, they seem to be the right choice. But to summarize all of that, there's no one method that fits them all. We have to be conscious as for what the requirements we have, and with that make the appropriate choices for the right method for the right purpose.
I was just going to say, I don't think I have anything to add. That was a very comprehensive overview, and I appreciate it. Thank you.
I have to admit, I heard the question beforehand, so I didn't come completely. I'm not that talented.
I would like to add that neurosymbolic and multi-representational learning is a very important kind of methodology. So you have information in some sort of a metric space, and that is typically machine learning, and which you compute a norm. And then you have information in the logical space where you have rules and you have logical elements, and there is some sort of an embedding where you transform or you embed the logical space and the metric space into some ways that can relate to each other. And as talked today morning, there's a bunch of hypotheses, and in order to, you don't need to satisfy all the SAT. You can use what's called as a partial SAT, and then this is a very good way of combining logical information, rules, and other graph theoretical knowledge with the machine learning kinds of knowledge. So I will move to the next question. This is for Jarvis. What is needed to build meaningful GenAI testbeds for science that include representative data sets, robust benchmarks, and full stack integration across platforms and workflows? Before Jarvis can answer, I'd like to say that last week, NSF announced a planning grants for the AI testbeds. They announced, I think, 2 planning grants. The idea here is that after this is fully implemented, the in a realistic situation to have test beds where the algorithms and methodologies can be, verified. So the first 2 planning grants have gone out, and that's the status of it. So Jarvis.
So thank you. So I think this sort of inspires me to think along a couple different axes, this question. So the first part is, when you think about test beds, I think this came up in a talk earlier this morning, and Lior mentioned this as well. There's this notion of that effective kind of testing or problem solving in general involves decomposition, right? Maybe we're all kind of victims of our own expertise in a lot of ways, that when we think of a problem, we often in our own minds synthesize it from the bottom up, and we sort of understand the full scope of knowledge, and we dive in as subject experts in our own areas. To me, and from my maybe anecdotal experience, I don't think AI is necessarily that. It is in some things, right? You can ask fairly detailed questions to get fairly detailed answers, for instance, with an LLM. But I think the most effective strategies that I've seen are the ones that decompose these tasks into smaller substeps. And I think this dovetails, like I said, that was mentioned in the talks this morning, with this notion of like unit testing that you might do in a software development scope, right? So you have your overall program or app or whatever you're writing, and you'd say, rather than sort of test end to end, you kind of write little tests for each piece. And I think something like that is probably also germane here. I mean, that would be my recommendation, I guess, would be that we have to think about this as an assistive technology that can help at intermediate steps. And maybe the onus at this point in time, maybe not in 5 years, but at this point in time, the onus on us might be to decompose it into those steps and look at the test bed kind of validation step as the sub-steps, kind of thinking about this incrementally. The other thing is that, as I kind of dwelled on the AI timeline, if you will, it was a nice overview this morning. I was sort of thinking, like, you can also characterize this into epochs or epochs, depending what your terminology preference is. So in some sense, like, we had several thousand years of human development where people created content, and a lot of it was analog and a lot of it was digital. And suddenly we had this big corpus of documents. And then we set out these language models and trained them on everything that was kind of existing in time up to that point. And that was maybe a first time step. And as was mentioned earlier today, they kind of stagnated until we put humans in the loop and said, okay, here's what we found, but is it any good? And then you could think of that as sort of one generation. It's sort of human generated content, computerized distillation of knowledge. Then you had another human interaction, and then maybe another computerized interaction. So I don't know how many epochs in we are at this point, but I would say we're, order less than 10, right? There's been a couple of these things. And I sort of see in my philosophy is that for these things to really kind of advance, to sort of validate these, I also see humans playing a crucial role, at least at the outset. Like I said, there's this tendency to think AI is going to automate everything for me. But I think I think we'll achieve kind of much more and at a much more rapid pace if we remember that this isn't just a burden to sort of inject ourselves into the loop. This is actually what gets to the next level, as it did with the first kind of reinforcement learning trained paradigms that we heard about earlier today. So again, my suggestion would be validation kind of at the unit level. I mean, I think we'll get to the system level, but I think to be kind of robust and precise, you want to kind of take problems, validate them in smaller times, in smaller chunks, and then also think about mechanisms where you can put the human into the validation process. I think that actually would end up benefiting more than the time invested, much as, the thousands of years of human knowledge being distilled into the first kind of GPT models, if you will. There's a lot of knowledge there, but it needs a next step, and it needs the next step, and the next infusion of maybe innovation that I don't think the models can provide autonomously just yet.
Yeah, so in a lot of the discussion, I think here and in general, we assume in machine learning problems that there's a large data set. We're going to train a model on it, do some testing. If it works better than everybody else, we brag about it, write the paper, and we're done. In many problems, it's not a one-shot process of constructing these data. For example, like NASA has airborne science campaigns, earth science campaigns, where they plan flights of, let's say, UAVs or even, say, a single large aircraft over many days. So they'll collect some data, takes a little bit of time, maybe a day or two, to assess those data relative to the Earth science models that they have. These are physics-based models, in some cases data-driven, and based on that, plan what next data collection they should do in the form of flights that they should conduct. So for test beds and benchmarks, ideally, and physical test beds, but otherwise virtual test beds or virtual labs where we can assess models for their ability to inform us on what additional data need to be collected, what gaps we still have in our knowledge, would, I think, be something worthwhile for appropriate communities to work on.
Thank you. So the next question is for Nikunj. How can GenAI support learning across different scientific domains with varying data availability, such as from well-instrumented fields like astrophysics to data-sparse ones like ecology or hydrology?
So seeing this question reminded me of NASA's vision for digital twins, and in particular Earth system digital twins. In addition to the roles I mentioned before, I do have a program management role on information technology for Earth science within NASA. And so as part of that, we developed this vision where the thought is that within Earth science itself, there are different domains that have mostly been stovepiped, which should not necessarily be. For example, atmospheric science and ocean science have mostly been stovepiped, but there is this, what is called a planetary boundary layer, where there is stuff going on where the atmosphere impacts the ocean and the other way around. So there's the thought that maybe if we have digital twins developed first by atmospheric science and also some by ocean science, then maybe we can plan to match them together and use those to help inform us across the two domains. That's just one example. There are probably other examples in other. I'm most interested in doing this within domains rather than across domains. Thanks.
I think, like in today's talk earlier, it's a fascinating talk, very nicely done. The issue comes down to representations, some sort of a mathematical representation for any particular domain one is talking about, and what all we learn from it. And then when we want to do the other domains, which doesn't have the enrichment of data availability, maybe one can go into a latent space and then use the models which was done there and transfer what all knowledge one has accumulated. Maybe this is one approach one can take. Any other?
Yeah, so I would like maybe to add on the representation. So it is probably really fundamental because we are trying to bring two somewhat non-consistent words of representations together, right? We typically have numerical data that can interact with itself in some manner, and we have symbolic knowledge that we want to somehow force to talk with each other. And you mentioned there were symbolic methods before and now representations. If we find a way to embed both of them in a common space where the two can exchange value, can exchange their level of confidence about either the data or the knowledge, because neither of them necessarily is correct, right? We admit that that was mentioned before. The knowledge can be wrong. We know that the Newton laws of mechanics are not correct. We have relativity, and we now know that that probably is incorrect as well. It is not consistent with quantum mechanics, so that's also incorrect, probably, right? So the knowledge is not necessarily correct. The data is noisy and sparse, and all of those things that we typically trash data to be. We need to be creative in finding some common space where the two can really interact and provide additional value in a complementary way. And it can be in a sequential manner, as we saw before in one of the talks about about having a loop with verification or validation that is a separate step after generation. Maybe there is even a better opportunity if we try to find a common space where they can exchange the value in the generation itself, right? So to generate and validate in the same one step.
Any other comments? So the next one is for Jarvis. What are the best practices for building effective collaborations between AI researchers and domain scientists? How should we train the next generation of scientists to work alongside GenAI tools?
So I think maybe I'll answer these kind of in reverse order. So the first one about training the next generation, I think to me, the main thing is just to kind of impress a couple core ideas. One is, again, this idea that these agents as of now are not oracles. So understanding what they are. Second is, again, this idea that I think all of us do, but maybe it's not as crystallized in our minds as it is when we kind of look at these kind of applications and the need for it, is this idea of taking big problems and decomposing it into sub-problems, not necessarily seeking the end-to-end solution. I mean, we all do this when we collaborate with people. We all know that there's different sub-problems that people are, qualified for or working on at this moment or whatever it is. So it happens all the time. But I think if you're training people that don't have that, partial lifetime of experience in this area, is to say, like, these are the methods that you want to look at. Divide and conquer, decompose and address, whatever you want to call it. These kind of methodologies that are fundamental to a lot of scientific disciplines, I think, are also going to be fundamental when using AI. And again, anecdotally from my own use cases, they just tend to work better when you can take your problem and decompose it into pieces and try to ask for assistance solving each piece. The other one that if I get up on a soapbox occasionally talking about AI, is that I think one of the things to keep in mind is that, I'll give an analogy. So, for a lot of us, right, a lot of our work requires calculations, but we don't do multiplication and stuff longhand anymore very often, right? So there's technology that can be a means to an end for productivity increases. And if I think about the next generation of scientists, right, so people that are younger right now are kind of coming up in an age when a lot of these things can be automated. You could say, write me a program to do X or whatever it is. And I think that incentive is a little bit mismatched, right? So for me, I kind of grew up in a mostly analog era, I guess. So for me, I could see that as being a benefit because I could do it myself the other way, but maybe it's more expedient for me to ask for assistance. I think the real challenge, and maybe a danger, if you will, is for the next generation to think about this as just a drop-in replacement for knowing those fundamental things, right? So we want to impress upon people that these should be technologies that are used to incentivize productivity, not to incentivize maybe laziness, for lack of a better word, right? That's a key thing, I think, that needs to be impressed, because for a lot of us, it came naturally by our upbringing. For the younger generation, I think this might have to be a kind of an artificial thing that that we teach. Best practices, I'll just maybe make a comment or two on this quick. Again, this idea, and I think Nikunj mentioned this earlier, that there are distinct expertises, in any discipline, right? So this mixture of experts idea, I think, is pretty pervasive, right? I think GPT-4, it's rumored to be using something like this, right? They train a bunch of individual models and use a mixture of expert type kind of aggregation. So I think that this notion of, we all sort of want a one-size-fits-all solution, but I think if you're thinking about how scientific, domain experts work alongside AI researchers, I think the goal should be, in my opinion, maybe thinking about building specialized techniques or specialized models perhaps for different disciplines. And then if you want the one-size-fits-all, there's ways of aggregating these after the fact. I think OpenAI is probably taking a similar tack, but that seems to be something that's far more scalable than asking for this end-to-end kind of solution.
Any comments?
As far as the first part of this question was about building effective collaborations between AI researchers and domain scientists. There's a model that I really like called the Frontier Development Labs. It's mainly run by an organization called the Search for Extraterrestrial Intelligence, or SETI. or SETI, but NASA has had significant involvement in this. It's an 8-week program in the summer, full time, where they have 2 PhD students or postdocs in AI and 2 in a domain science, and they work together full time plus for 8 weeks and come out with some, paper or presentation. Oftentimes they have published their work as well. This is just nice because they're full-time, fully engaged in this. Since they're PhD students and postdocs, they don't need a lot of sleep. Just give them pizza and they do great work. And I have found that a lot of what's produced, actually, there's a lot of future work also left in there. And those can be good, that can represent good material for grant proposals. And that's also a good way that, the people, they really learn about not only specific considerations of the other domain, but generally, let's say, a different way of thinking. And that's a good thing for people early in their career to gain.
Actually, I did my PhD here at University of Minnesota, but I did all my research at Mayo Clinic. And this was a very good model. The model is the student is the integrator of knowledge between the 2 different advisors. And I would teach, the domain scientist, the AI and the computer science part of it, and vice versa. So I think I like this model very much. Okay, I will go to the last question for Lior. And what are the most promising short-term applications and long-term challenges where GenAI can accelerate discovery? Can GenAI meaningfully assist in scientific creativity, literature synthesis, or hypothesis generation, even when mechanistic understanding is limited?
So I would even start before we get into literature review with the first step that we hopefully do when we start engaging in a scientific problem. We ask a question, right? So how do we form a question? There was a very nice work of DeepMind in guided intuition. What they did was effectively they brought from node theory, there are different nodes with different algebraic characteristics, different geometric characteristics. They just put a neural network between them and try to predict one from the other. And even though they did not get an explicit relation that explained why one algebraic characteristic of a node is similar to a geometric one, they did find some implicit relations that sort of give you the intuition, oh, this is an interesting question to explore, right? So we can see that already with asking the right questions, we can use GenAI to ask such questions. We can use GenAI also to provide us some guidances for what are the edge cases of each theory, where things do not work very well and maybe we should explore further. The next step is, of course, the study, right? And in the study, obviously, GenAI can be very, very effective at aggregating, even curating and providing some sort of scaling as for what type of prior data and knowledge we would like to incorporate as some prior knowledge that we bring into the discovery process. Jarvis was mentioning the composition, right? So we see some relatively new and exciting ideas as for how GenAI can even do some form of decomposition, a chain of thoughts, a graph of trees, a chain of graphs, a graph of trees, and so forth. There are different ways that we can take a problem and decompose it hierarchically or as a graph. And now AI can do some of that. And potentially that can help us even when we try to challenge a very complicated problem. How do we even start? It's very difficult to charge all the aspects of the problem in one go. If we can decompose it into some smaller, loosely coupled components and address each of them independently, maybe this is something that is more manageable. We can also distribute such a problem with other agents. It could be human or they can be AI agents, but this is enable us to scale also in terms of the number of entities that tackle such a problem. One topic that I guess we all have already saw is that obviously GenAI can be very useful in hypothesis generation. It can be very creative. Sometimes we trash the hallucinations of GenAI as a negative component. It can, if we embrace hallucinations, that can also help us, right? We may want to be as creative as conceptualizing that the time is relative, space is relative, but speed of light is constant. You need to be hallucinating a little bit to come with such proposition and come up with relativity, right? So hallucination is not something that we should regard necessarily as a negative component, as long as it is coupled with a formal method that can verify that we throw a lot of darts now, we then come and see which one of them actually fit into our target rather than just keep on throwing them, right? So hypothesis generation can be one of the near term, or already one of the near term usages of GenAI. Of course, it can be useful in experimental design and in the art of hypothesis testing. We may want to think about using GenAI for augmentation of rare events. So oftentimes we would like to explore specific scenarios in our distributions that are a little bit at the edges, and GenAI can help us to generate such data sets, and then we can explore them. And of course we can do analogical reasoning. So we may be able to bring some concepts or rules or ideas from one topic to another by asking about analogies, and typically we can get interesting, at least interesting results. The last one on the short term is something that we all do. They can be very, very helpful when we write a report, right? We can use GenAI to write our papers or to write a report to the NSF or other agencies. So I guess I'm not telling anybody a secret here. The long-term challenges are a little bit more tricky, right? So part of the challenge is how do we deal with multi-scale type of problems, or multi-physics, multi-scale. And here you may need to incorporate simulation and physics of different forms in one coherent, in a multi-scale, right, in one coherent framework, and that is challenging. Causality is also something that for now, I believe is a little bit more challenging, especially with complex systems. We would like to be able to bring the theory and the data into one unified space where they can talk with each other, and that's currently a little bit outside the realm of what GenAI can do. And the last thing, maybe again related to theories, is it may be at some point we now have, in addition to large language models, we have large reasoning models. Maybe they'll be able to generate some propositional theories or at least serve as a first gatekeeper for some of the hypotheses we have. And then those that pass that secondary, let's say, or the primary filter, those that pass that, we can actually delegate further into formal methods that are computationally very expensive, right? So we can think about it as a two-tier filter, right? The first filter would be large reasoning model. Whatever past that, we will take into a formal method that will do a more rigor type of analysis.
Yeah, well, one other advantage is what if out-of-the-box thinking, these are very easily done by these sorts of methods, and those are invaluable, right? I mean, these are how we can expand the creative dimensions. So I think the question for the panel is done now, and I think we can ask the rest of the audience to ask questions for the panel.
Yeah, thank you again for that interesting question and answer session from the panel. One of the questions I have is in terms of cross domains, like when you're talking about discovery. Discovery is one of the things, or any scientific experiments that we do. So if you want to discover something, or if you want to come to we talked about hypothesis and things like that. So there needs to be this change of reframing, actually, the problem itself in many sense. Like you go from one domain to another domain in one, like Nobel Prizes were won by people doing multiple levels of abstractions they go through from the quantum mechanics stage to actual doing the biological analysis kind of thing. So this whole notion, how good are the systems right now in doing these kinds of things, where you kind of grow across domains from one domain of quantum mechanics probably to another domain, the domain of biological enzyme reactions. So you have to kind of go through this, jump across these various domains. And how good are the current systems in terms of using this generative AI?
I can give you
When are we going to go there?
Yeah, no, that's a great question. I can give you my few cents on this one. So obviously, this is one of the more challenging problems because we are dealing with very different scales, right? From quantum level scale to more of a macro level scale. We both in space and time, right? So the length of the reactions and are much slower on the biological level versus on the quantum level. And the other challenge is the degree of, I would say, predictability of those laws, right? So we feel a little bit more comfortable to put a heavy foot saying, okay, physics is physics. There are some conservation laws. We almost feel very comfortable to say they should strictly be honored, while in biology, we often have some processes that occur with some degree of stochasticity or maybe even with some chaotic behavior. And there is a very different degree in which we can expect to induce or deduce some hard coded laws on the biology side compared to, let's say, the physics side. I believe that GenAI can help us to bridge that gap slowly. It will take a lot of time because we need to build a bridge after a bridge, right? We start with maybe with the more fundamental physical laws. We would build a bridge to chemistry, where that's the nearest, let's say, a science that where we can see how physics become, manifests itself in reactions and so forth. And then we'll have to take another step into biology. I don't know of any other simple way to do this sort of leap, but maybe some of the ideas that Jarvis mentioned about the composition can help us to even bridge that in a different way, right? So this is not a linear bridge. Maybe this is a bridge that requires bigger jumps.
What's the timeline here?
It's a question, what are your expectations in terms of fidelity, right? Because if your expectations are relatively modest, we are already there, right? We already employ GenAI in biology, in chemistry, in physics. We get reasonable results. Some of them are useful, right? So when it comes to maybe the bottom line question, is it useful? Yes, we get some models that are useful. Are they consistent? Maybe not fully consistent from scale to scale. And this is where I believe that we need to bring that bridge, right? So we can come up with models that are phenomenological, they are not fully derivable, right? So this is where I put maybe the divide, right? We have models that are derivable, are things that we all feel very, very comfortable, right? We would start with a set of axioms and we deduce a new law that we say, okay, it is really completely dependent upon those axioms, and I feel very comfortable with what that model is. That will be much more challenging to get to. We do have models that are induced, right? We bring a lot of data, we bring some knowledge, and we try to make everything work together. I believe that this is more of a gradual process until we will be able to bring more and more of that knowledge and the data to tell us with higher level of fidelity how those processes in biology, for instance, are related to the fundamental, let's say, quantum mechanical processes.
So
Probably one possible methodology could be that domain foundational models, if one can concatenate them and one is allowed to change them, and you can tailor these to get the kinds of models you want, right? I mean, that would be a good way to do it for future.
Yes, one thing in the test. Yeah, one thing I think in the advancement of science is hypotheses are proposed and often proved to be wrong. And one wonders, in fact, their wrong hypotheses are hard to publish. And so that might point to a place where GenAI could think about how wrong hypotheses would be developed within this framework as well, because we wouldn't want to be throwing out ideas that avoid dead ends in the advancement of science.
I can comment quickly if I mean, so I believe that there is a big question as for whether you find other viable hypotheses in the vicinity of one that is wrong, right? So if you think about it as maybe as some sort of geometrical space of hypotheses, are there, and we see that in combinatorial optimization and other domains, right, where we have a solution that is not optimal, right? Is there another solution that is optimal in the vicinity or not? And in some domains, you actually find that you may find one, right? So it's the fact that your hypothesis was wrong doesn't necessarily mean that you need to completely abandon the entire branch of exploration. You may be actually very close to something fantastic, amazing. In other problems, they seem to have a very I would say erratic underlying topology of how consistent or inconsistent such a hypothesis is with the data and the knowledge, and a search in the vicinity of such hypothesis will not really lead you to anything meaningful. And it's a good question. How do you characterize your hypotheses and the space in which they live in, right? Is it worthwhile for me to do a local exploration next to an incorrect hypothesis that apparently was not that bad because I arrived at that, so I had some guidance, or we should just go and complete the exploration.
And wrong hypotheses can be a constraint to avoid dead ends. And so it seems to me a little thought to that might help.
Absolutely, absolutely.
So I was just going to comment that it was a really kind of insightful thought with your question, and it kind of made me wonder how the performance of these models would be different right now if the literature contained a lot of these instances of false hypotheses, right? So the coin of the realm, so to speak, for us advancing science was always kind of hopefully positive kind of results that would build on a foundation. But we now see things like if you do image generation with, stable diffusion or whatever, there are negative prompts, right? So it's like, here's what I want, here's what I don't want. And I think that both sides of the coin are kind of equally valid in this context. And that's a really kind of cool idea.
Hi, thank you for the panel. I have a two-part question. One is the concept of the test bed itself. What are we testing? So if you look at the test bed, the way that these GPTs and all those are released every few months, what are they testing? What are we trying to test at what level? That's one thing. And second, the intersection of domain is where the actual innovations happen. From where I come from, energy, water, material nexus, and the intersection between them. And then one of the biggest problems we are trying to solve is the energy for data centers. How AI is going to increase the energy implications for that. So energy for AI and AI for energy. So those are the two things. So if you want to develop such a test bed, and what is that we are trying to test? And can you ask ChatGPT to generate its own test bed? The reason I'm asking that is, if you're trying to benchmark something, most of the algorithms may work and show that it is working very good for that particular benchmark test. But if you want to do something much bigger in concept of a test bed, what are we trying to achieve in the test bed? So I didn't get the concept of what you mean by test bed in this. So just a clarification question.
So I can give you my understanding at least. So when you look into the scientific method in general, right, there are two possible ways we can go about that, let's say, arc between hypothesis generation and hypothesis testing. One is a deductive form, right? So you bring your knowledge, you articulate all the axioms and background knowledge that you have, you deductively derive a relation, and then the testing is really about making an experiment that will empirically validate that what you deduced is indeed correct, right? So that's one passage that we historically actually had many of those. In the recent days, we actually go in the opposite direction, right? So we are take the data and we let the data drive, I think, as you said in your talk, and we induce from multiple instances a hypothesis. That hypothesis may or may not be consistent with the background theory, and then the testing is actually against the theory, right? So that's a completely different direction compared to deductive, where you go from the theory to the validation, to the empirical validation. You go from the data, you identify patterns, you then form some hypotheses, and then you do some validation against theory. Both arts are important and equally useful. I believe that it depends really how much knowledge you have, which is trusted in you, and how much machinery you have in order to deduce such hypotheses versus how much data you have in order to induce hypotheses that are meaningful. So to your question about doing that in the energy domain, I assume that the law of physics are relatively well established, right? So in a sense, you are standing on relatively firm ground when it comes to at least not complete, but relatively complete knowledge of the background theory. The challenge is typically maybe in the experimental validation. I don't know whether you do it fusion energy and you want to measure what, I don't know, what is the yield of such system under million Celsius degrees and unbelievable pressures. It's challenging to even come up with a proposition as for what is the experimental design. How do you build the right platform and the right pedestal and all the elements that are needed in order to make an experiment that will provide you insight or meaningful understanding as for how correct was your deduced hypothesis. But I hope that I answered the right question. Maybe I didn't.
If you're talking about verification and validation, verification is about, are you doing things right? Validation is, are you doing the right thing? So the physics of the problem. When you're talking about data-driven approaches, whether it is for predictive or discriminative AI, there is no best practice. That is one of the biggest problems is generalizability and repeatability of these models. Where I sit, I get hundreds of proposals saying, I put sensors, collected data, here is the prediction. And then put sensors, collected data, put some. So there's no way that we can generalize that, repeat it, and there's no best practice of how you trained it. What is the verification? What do you mean by validation there? What are we testing? So those are the questions I am trying to get at, because we have developed a lot of test beds at DOE at various labs. And each of them, when we develop the test bed architecture, we go with a clear idea of what are we testing, why do we test, and who is validating it? Is it human in the loop, or it is validating itself? So those are the questions I was trying to.
Right. So obviously what goes into the test bed is like what domains are considered, what types of questions are featured, have pretty big downstream consequences for what the focus is on. And I would imagine there's kind of this balance between practical concerns such as readiness for a certain domain to provide easy to work with data and questions, and then also probably something like the societal impact of what progress could mean. Could you comment on what goes into those decisions for kind of recruiting domains into test beds, and also how you deal with the varying degrees of say, fragmentation in a certain domain that might make practical uptake in early days quite a bit more challenging, despite having a lot of value if progress is made?
So in one of the proposals NSF funded on the test bed, I think it was to Cornell for agriculture, if I'm not mistaken. And I think the idea here is they had a bunch of issues in which the agricultural scientists needed to address, and the main concern, the main reason to build this test bed, or this is just a pre-proposal for saying what the test bed should be. Anyhow, the main reason to fund this was to say that in a realistic situation where the agricultural research and production is going on, what are the various issues that needs to be addressed, and can this test bed emulate those circumstances? That was one of the main concerns. And then the next concerns is what are the algorithmic issues, what are the systems issues in order to realize those goals.
Hi, I have a question. I'm Jigyasa. I'm a PhD student here. So to tackle some complex problems, we have so many methods to tackle. So to tackle the small parts of that complex problem, we might have a variety of methods which are like completely different from each other. But sometimes these methods who are handling different parts of that big problem become so intertwined that it's difficult to gauge which method is contributing towards the like improvement at the end results. So especially when you don't know what to expect at an intermediate state, and also maybe for the sake of compatibility, you have to change multiple methods at a time. So I understand that this is a very general question and it depends from problem to problem how to handle this. But if you could share some thoughts about it. And a follow-up question to this is that how important is it to have these reports of individual method performances for the community?
Maybe that also relate to the previous two questions. So I'll try to provide a useful answer here. In other domains in AI, we typically have benchmarks, right? And these benchmarks are well-defined set of problems and data sets that we can bring our best method and see how it pars against other propositions. And that seemed to be a relatively well-defined yardstick that we can do all those comparisons and feel relatively comfortable about it. When it comes to the scientific domain, we typically have problems that have a stronger sense of realism, right? So the data is real. It's not some artificial benchmark that somebody created in the lab, right? We have a greater diversity of problems that we tackle, right? So it's hard to settle upon, here are like 5 problems that we all agree that this is what we all do together, and if we score best on those one, we are doing well. And maybe the other question is indeed, how do we characterize the methods we use, to your point, right? In terms of their contribution to uncertainty, to errors, to other either positive or negative artifact implications of what we are trying to do. And one way to try to address it is a community effort, right? If we try to come up with a unified set of even a language, right? So how do we articulate the theory in one unified language? We can use systems like Lean from Microsoft Cog. There are other Isabel, other formal methods. But if we agree as a community, let's all use one of them and articulate all the background theory in that language, at least we have one consistent place where we know that at least the definition of the background theory is one, right? So you will not have to translate from one problem to another and say, oh, you changed the name of the variable, and therefore, I didn't even understand what you were doing, but both of us were trying to do conservation of energy, but it was not obvious that we were trying to address that. So on the theory side, I believe that it is relatively maybe more amendable. On the data side, I guess we will have to build up some hierarchy of different problems and understand what each data set attend to. And if we bring a little bit of order and discipline into doing that, maybe we have a hope to learn from each other, because otherwise each of us is doing its own point effort, get a paper published, maybe do something locally meaningful, but it doesn't scale to anything beyond that. The moment we have some unified repository of models, of theory, of data that as a unified format, right? There is some discipline. Potentially, we can take that to the next level and build upon each other's. Also, to your point, mistakes and successes.
Yeah, so certainly Lior's, points are, quite good, really, so in this case, focused on, it seemed like focused on the data, the algorithms that say things like accuracy, but then there are domain-specific considerations like, what is the potential payoff? Do you need a quick answer and let's say a quick and dirty answer is good enough, or do you really need to take more time to get a more accurate answer? Let's say, do you have sufficient compute horsepower, disk storage, whatever it may be, for your particular problem? Just it calls to mind, to make it a little bit concrete, we have looked at in aviation safety, let's say radar track data, but only when the radar track data look anomalous do we bother to pull up voice recordings, because it's the vast majority of the time nothing interesting is going on, so it's not worth hogging all that disk space for those recordings. But of course, that means the voice recordings that you're pulling up are very skewed towards the cases where something abnormal is happening. So you have to account for that in your method. And so you have to deal with all those practicalities as well, which, as you said, is very domain specific.
We're out of time, but I think what was the most interesting part was the set of questions people ask. I think at this early stage in GenAI, we don't have to have the answers necessarily, but we should be asking the questions, and the right sort of questions is what's going to drive the field, right? So it's perfectly fine for us to stumble on the answers. It's just that we just have to formulate and continue to keep formulating questions and challenge us ourselves. So I would say let's thank the panel. And we're going to break for lunch, and we'll be back here at 1 o'clock sharp. And I think Paul Hansen is going to moderate the next panel. Thank you.